Hello everyone. This is our first lecture, our first attempt to understand Kirchhoff's voltage law, or KVL. In previous lectures, you have seen Kirchhoff's current law as one fundamental law, at least as far as circuits are concerned, for currents. Kirchhoff's voltage law, on the other hand, is the main tool we will be using when we try to relate voltages in a circuit. In a similar way that Kirchhoff's current law is derived for something more fundamental, that was the conservation of charge, Kirchhoff's voltage law is also derived for something more fundamental, and that's the conservation of energy. So first I would like you to pay attention to the basic physics principle. I will give you a quick reminder, something which I suspect you have heard before, and then we will see the math expression for Kirchhoff's voltage law when we try to apply it to circuits. All right, so first the basic physics principle. The basic physics principle is that when you integrate the electric field along any closed path, the result must be equal to zero. So let me say this again. When you integrate the electric field, and to be more precise, the electrostatic field, along any closed path that you choose, the result will be equal to zero. This is a basic law of electrostatics, and you might wonder, why is that true? Well, let's look at this scenario. So let's say that I start from point A. I basically go ahead and move a charge, and I bring it back to point A, exactly the same point A. I then will have moved a charge in a closed path. If I were to basically find out how much work I have done, which would have been integrating the force on that closed path, the result actually will be equal to zero. Why is that? Well, my charge in point A had some amount of energy. When I'm basically moving it around along different locations on this path, I'm spending some work. That work is F dot dl. And when I complete that work and I bring the charge back to point A, I expect the charge to have the same amount of energy in an electrostatic field. And because the force that I have to apply is at the minimum equal to the charge itself times the electric field, I get the result that you will see right here. I know I'm covering this fairly quickly, but as I said, this is a basic physics principle which we will not focus too much on this class, and I know that you have seen that before, or if you haven't, I'm pretty sure you can find it online very quickly. The main thing is, again, the electric field integral on a closed path is equal to zero, and from there we can actually write the math expression that is going to be really important to us, is the fact that the sum of the voltage drops across any closed path will be equal to zero. Now, why is that? Is because the voltage is actually related to the integral of the electric field. This is something that we have talked a little bit before, but you can also find it in basic physics books or electromagnetics textbooks or online. So I won't really go too much into that detail either. But I do want to spend a little bit of time finding out more about the expression that you see here. So first of all, let me restate this expression. The expression says that the sum of all voltages around a closed path must be equal to zero, must add up to zero. First of all, we're talking about summing voltages, and if I want to be slightly more precise, we're talking about summing voltage drops. The second thing is that this must be true for any closed path, any path that you like. The third thing I'd like to say is that this path may or may not include circuit components. For example, let's look at this little circuit that you have here. One closed path is to start from node A, go up to point B, go right to point C, down to point D, and back to point A. This is one closed path, and every branch of this closed path includes a circuit component. But there is another one. I can go from point D up to point C, point F to the right, E down, and back D. This closed path has essentially branches that include some components, but also it has this branch here from F to E that does not include any components. Both of these paths must satisfy KVL, that the sum of the voltage drop across this path must be equal to 0. Also, you could choose another path. You could go from A to B to C to F down to E, D, and A. Here's another closed path. It doesn't have to be the smallest path that you see in front of you. Any closed path, KVL must be true on. All right, now let me give you a little bit of an example. How do I apply KVL in any circuit? So the first thing that you have to do is that you must write down the voltage drops that you would like to apply KVL on. After all, the law said that sigma of Vn must be equal to 0, where Vn are the voltage drops on a closed path. And the same way we've done for currents, where we have to assume a direction if we don't know it, we also have to assume a polarity for a voltage drop if we don't know it. Now, as I have mentioned in the past, if you don't know the polarity of a voltage, make an assumption and don't worry too much about what polarity you're assuming. So here is the polarity, for example, which I will call V1, and it is the voltage drop across the branch AB. Here's the polarity V2 that I will assume across the branch CD. Here's another polarity, which I will assume V3 across the branch CD. You could choose any polarity you like. The final result will be the same. And you should not worry about it if the assumed polarity is not the correct one. Your final result simply will end up having a negative sign. But once you commit to a polarity, like I have done here, you must apply KVL correctly. Now, how do I apply KVL correctly? There are many different ways you can do it, but this green box that you see down here should really give you a very consistent way where you can do it every single time. As I have mentioned before, it's extremely important to apply laws consistently so you don't make mistakes. So let's see the three very quick steps that you can make to apply KVL. So step number 1, start from the lowest left corner of the path that you like. I'm going to first go for this path here, A, B, C, D, A. The lowest left corner is point A. Of course, if you don't like to start from the lowest left corner, pick another one. Pick the upper right or pick the upper left. Pick any corner you like, but always pick the same corner and always apply from the same starting point. I like the lowest left one, and I will always apply KVL from the lowest left one. Now, after we do that, we have to choose a direction. I always like moving in a clockwise direction on my circuits. If you don't like clockwise and you'd like to pick counterclockwise, that's fine too. Just make sure you stick to the same direction every time. Don't change it based on how the loop looks like or how the circuit looks like or how you actually feel that day. Always stay with the same direction. For me, it will be clockwise. Step number 3, down here, always start with the first voltage sign that you see. See, when you move along the closed path, for example, in my case, I'm moving from point A towards point B, I will always see a voltage sign. It will be either minus or plus. In this case, it will be minus. So that means when I account for the voltage drop across the branch AB, I will basically write it as negative V1 because the sign is negative in the direction I'm moving. The first sign I encounter is negative. So now moving on from B to C, I encounter V2, and V2 I encountered with the plus sign, so I will write this as plus V2. Finally, I'm going from C to D, and the first sign I encounter is negative, so it will be negative V3. And finally, this is equal to 0 because I'm arriving at point D, which of course is the same as point A. So here is a successful application of KVL on the closed path A, B, C, D, A, starting from the lowest left corner, that was rule number 1, moving clockwise around the loop, that was rule number 2, and finally using the first sign of the voltage drop I encounter to give a plus or minus to this voltage. Let's practice a little bit more, and now let's choose this path here. So the ABC FEDA path is this long one. So ABC FEDA path is this long path that you just saw. So I will go ahead and signify a couple more voltage drops, which I don't know, so I will hypothesize them. So let's say that I have plus minus here V4. This is the voltage drop from C to F. Let's say that this will be here V5, the voltage drop from F to E. And of course, node E is the same as node D, is the same as node A, so there will not be any voltage drop between these nodes. So again, I'm starting from my lowest left corner. This is corner A. I'm moving clockwise, so once again, I'm going to go from branch AB. The first sign I see is negative, so I'm going to start this with a negative sign, so that will be negative V1. Then I see V2 with a plus sign, so this will be plus V2. Then I see V4 with a negative sign, so this is negative V4. Then I see V5 with a plus sign, so this is plus V5, and that's the end of it. I have arrived back at node E, which is the same as A, and therefore this must be equal to 0. Now, of course, the first step is doing what I'm doing right now, applying KVL correctly and consistently every single time. In real circuits, what would happen as a next step, and this is something we will see in examples, is that some of these voltages here will be known. Perhaps, for example, the voltage here is known. V1 is maybe 5 volts. Some other voltages may not necessarily be known, but perhaps they can be found by applying some other law. Perhaps, for example, V3 here, we may be able to find it by applying Ohm's law. The point is that once we have enough equations from KVL and perhaps KCL, we can solve the circuit completely, and we will see examples of this next time. So perhaps I would like to finish here this lecture by pointing your attention once again to the need to learn KVL and apply it consistently every single time, so you're not searching for what you're doing, but rather applying your KVL correctly and consistently. So thank you very much. We will see you next time.